Welcome back, ladies and gentlemen. Today we're going to talk about static and kinetic friction. Hopefully at the end of this video you'll have an idea of what causes friction, what static and kinetic friction are, the differences between the two, the situations in which each apply, and some of the rules that govern friction. So we generally understand friction pretty well as part of our day-to-day lives. We know that if we push a book across the table, it's going to experience some resistive force. We know that if we slide sandpaper across something, there's a greater resistance force than a smooth surface. But one key point is that friction always occurs between two surfaces. We know that it is a contact force. This means, pretty straightforward, you cannot have a frictional force on two things that are not in contact with one another. When we talk about air resistance, it might seem like it's not a contact force, but in reality, it is the molecules of the air contacting whatever surface they're coming up against. So you must have two surfaces touching contact to be a friction force. So it acts parallel to the surfaces in question. So if we have two surfaces, we have a box and a table. The frictional force cannot be in any of these directions. It is simply not possible. None of these are true. The only way friction can act is parallel to the two surfaces. Parallel to the two surfaces. And friction at the microscopic level is caused by molecular bonds, bonds between the molecules that exist at the surfaces between the two objects that are in contact. So what does this look like? So we have two surfaces here, we have two blocks, and think of it like a smooth table and a smooth book. We think of these as smooth to the touch. We can slide our hands along them. They don't feel rough necessarily. However, there are microscopic contact points. These surfaces are actually, on the microscopic level, very rough. So there are lots of little imperfections. You can see these little peaks in here, right there. And when these come into contact with each other, they form bonds. They form chemical bonds between the elements in the two surfaces. And these bonds require force to break. You have to apply force to break these bonds. On the microscopic level, that's what's happening. You have these tiny little contact forces, these tiny little contact points that require force to break. So we can make the next logical leap and surmise that friction is increased proportional to the normal force. So again, friction is increased proportional to the normal force. Now, a normal force, we know, is the force that one object exerts on another object perpendicular to the contact. So we have two surfaces in contact. Okay. We know that this is the normal force. This is a normal force. These are perpendicular. And these would be the frictional forces. Frictional forces, okay? So the perpendicular force has to increase. So the normal as the normal force increases, let's look at what happens. So with a low normal force, we might have this little contact point, right? If we push a little bit harder, we can see these two coming into contact. If we pushed a little bit harder, maybe we'd have something going on over here, right? But on a microscopic level, with low normal force, a small normal force, we only have one contact point in this little area. However, with a very large normal force, if there is a lot of mass up here pushing down, acting in a downward direction, then we have a lot of little contact points. We have one here, we have one here, we have one here. We might imagine there was one here, some over here. So what this means is that if there's a large normal force, we have a lot more contact points, and this equates to a lot more bonds. So more microscopic contact points are close enough to form bonds with each other. So the more normal force there is, the higher number of bonds you'll have, and the more force it's going to require to get rid of those bonds. Okay? Let's talk about static friction. So static friction only applies to an object at rest. Only applies static equals rest. Okay? Static at rest. So static friction only applies to an object at rest, and it increases in magnitude with the applied force up to a maximum value. So if I push on the box with 5 newtons, so if this is 5 newtons, if the box does not move, this must be 5 newtons. Why is this so? So when we say at rest, this means that the acceleration equals 0. From this, we go straight to Newton's second law. Sum of the forces equals mass times acceleration. This is 0. This must be 0. And if the, I'm going to come down here, if the sum of the forces is equal to 0, then force applied plus force of friction must equal 0. Therefore, force applied equals negative force of friction. This means that they are equal in magnitude and opposite in direction. We can see equal in magnitude, opposite in direction. Cool? So if the friction goes up to 10, if I push, if the applied force goes up to 10 newtons, the friction has to go up to 10 newtons. Caveat, up to some maximum value. Up to some maximum value. That is the key word here. Key word, maximum value. At a certain point, we are going to hit that max value that is determined by a coefficient of friction, which we will not touch on. But once we hit that maximum value, then that static friction is broken. So after the maximum value, static friction is overcome and the object begins to move. Okay? The object begins to move. And after that, if we're no longer at rest, then static friction no longer applies. So remember, if we push with 5 newtons, the friction is 5 newtons. Okay? And, like we said before, the maximum value is dependent on the normal force. Okay? The more normal force we add, the higher our static friction value is going to be. So a heavier box is harder to move than a lighter box. Kinetic friction. Kinetic means moving. Kinetic, moving, kinetic, moving. Once the object is moving, then kinetic friction applies. And here's the difference between static and kinetic friction. Kinetic friction stays at a constant value no matter how much external force is applied. Okay? So, this is determined, again, by some coefficient of friction. So, if F applied is equal to 10 newtons, say the force of friction is equal to 10 newtons. Then our velocity is constant. Okay? from this. So if the force applied is 20 newtons, force of friction is still 10 newtons. Still 10 newtons. So this means that the sum of the forces will be 10 newtons, and the acceleration will be greater than 0, non-zero. And then, similarly, if force applied is 30 newtons, force of friction is still 10 newtons. And acceleration is greater than 0 once again. Okay? So, key points: stays at a constant value no matter how much external force is applied, but it is, again, dependent on the normal force. So it does change depending on what object you're talking about, how heavy it is, how much normal force there is. But if that normal force does not change, the static friction will be the same. So our final takeaways: static friction increases with applied force up to a maximum value. Once an object is moving, kinetic friction applies and is a constant value. And both static and kinetic are proportional to the normal force. So thanks very much. I hope you got something out of this. If the quiz is still up, make sure you go and fill that out, and that will be turned in for a grade. If you're coming back to review this video because you forgot about friction or you're studying for a quiz or test, good on you. Yeah, make sure you fill out that quiz if it is indeed prudent to do so. Thank you for watching.